glorious day and call it proteins and enzymes. Beer's law is also in this particular unit, so those of you who said you never learned that, this is the place where we learn it in chemistry. It's only in the option. Beer's law again says that the absorbance, or the amount of color, is directly proportional to the concentration. We will be talking about Michaelis-Menten kinetics. Yeah, I'm pretty excited, but I'm also really underprepared. Really thought today would be play test. We will talk about competitive and non-competitive inhibition. The internet and the textbook don't totally agree on what non-competitive means. I did look up uncompetitive for a side conversation we had. I'm ready for it. So I'm curious what you say. Always curious. We're going to talk about buffers. The most important thing that Margaret's going to take away from the buffer conversation is that the Henderson-Hasselbalch equation is in your data booklet. It is listed as a part of B. So if you find yourself trying to use it on paper 2, you are not doing the right thing. The only time we use Henderson-Hasselbalch is in B. And so expect that there's probably a question in paper 3 about Henderson-Hasselbalch. This should look kind of familiar. So we have an amino acid and we have it in its Zwitter ion state. Remember, in the Zwitter ion state, the carboxylate has a minus and the ammonium has a plus because the acid has donated its protons to the base. We know that we can remove another electron from this and make the conjugate base. We know we can add a proton to this and make the conjugate acid. The Ka is the equilibrium constant that's associated with taking an acid and having it lose a proton. And so we can describe this step in terms of a first pKa, or Ka, and this step in terms of a second pKa, or Ka. Again, because the acidic state, or the cation state, can lose 2 protons to go to the full anion state. Bueno? At the pi, which or something that has a really simple R group that's just the average of these 2 numbers, we expect most of the stuff to be in this form. Honestly, we expect all of it to be in that form. So many words. So if the pH is less than the pi, what state would the amino acid be in? Okay, it's going to be a cation, so would it be going toward a negative or a positive side of a gel electrophoresis cell? Negative side, excellent. Could you write the chemical reaction that's occurring if we added some Zwitter ion? I'm going to draw my way. If I were to try to convince you that this by itself is actually able to buffer, what would I have to show you about it? So typically I have to write 2 chemical equations showing the effect of adding small amounts of acid or small amounts of base. So here I take that Zwitter ion and I'm going to add a small amount of base. And I'm going to find that this weak acid reacts with that strong base to make what? Water. And its conjugate base. And so effectively, what if we turned the weak base into? Take a salt, but I'd also take weak base. We've taken a strong base, and we've converted into a weak base. Would that work if I added a whole lot of hydroxide? No, because if I added a whole lot of hydroxide, after I've converted all of this into its conjugate base, I'm still going to have hydroxide floating around. We could write the reaction of this with acid. And one more time, we're going to make water, and I'm just going to write the word cation here because I think that you can see it. So I was trying to make these equations a little bit more lifelike by writing them out structurally. You should be able to take that Zwitter ion and add acid or add base to it and show that it has some perhaps buffering capacity by converting the strong acid or base into the weak acid or base. Is anything awful yet? I feel like we're getting warmed up. Felix adequately unhappy. Smile, like I don't know. Just don't look happy, even with the smile. So this is that very popular Henderson-Hasselbalch equation. I want to remind you where we get it from. So let's go back in time to topic 18. And remind ourselves that ethanoic acid is a weak acid. So in the presence of water, it will donate a proton to form hydronium, thereby lowering the pH of the system. The pKa of this is 4.75. If we had an initial concentration of 0.3 molar, so that no one knows the answer, Lord knows I don't, could we figure out what the pH is at equilibrium? Yes? So do it. that? Did you take the square root? Did you? Yeah, that's what I got. Yeah, I think you forgot the point 3. Well done. Good? Okay, so I used my fancy red pen to show the approximation that you made. You made the approximation that the amount of stuff that would hydrolyze was small compared to that initial concentration, and I think it's not a bad approximation. It's about 1%. 1%. Lots of photos being taken. So maybe a way I could show you what you did is I could rewrite this expression. I could say that when I solve an acid problem, what I typically do is I use the initial concentration of the acid in the denominator. So that's all that 0 means, is that it's the initial concentration. It's saying I'm not going to worry about this minus x, I'm just going to throw the 0.3 in there. And to make a sad but tired point, most of you on the test just wrote that H3O plus was the square root of K times the initial concentration. Like you knew where it came from. It comes from right there, and the fact that these two values are equal. So in some part of the world where they generate IB mark schemes, this is the way they show it. So if you've looked at any past paper questions, that's how they do it. It's just not the way that we have done it. That's okay. If I wanted to make this a buffer, what would be different about the system? So this stuff could absorb hydroxide to make a weak base, ethanoate. Could it absorb acid? No. There's nothing there to protonate. So it's not a buffer because it can't meet our definition of buffer. Our buffer was something that could resist a change in pH upon the addition of small amounts of base or acid. And I tried to show you how that might work. When you add a little bit of base, it's like, yo, I'm going to take that base, I'm going to eat it, and I'm going to make weak base. Yo, I'm going to take that acid, I'm going to eat it, and I'm going to make weak acid. That's why my pH isn't going to change. Over here, you might argue that this is able to eat the hydroxide and make a weak base, but it doesn't have the ability to go the other way. So what could I do to this system to make it absorb H plus and turn it into weak acid? I feel like we have a practical definition of a buffer and the textbook definition. So the textbook definition is the two equations on that and a solution with the ability to resist pH upon the addition of small amounts of acid or base. So that's how I get those marks in the buffer question. That's a paper 2 question. But the multiple choice, the paper 1 question is, yo, how do I make one? What do I need? What ingredients does it take?
So is it like you have a certain amount of like weak acid, but then you need like half the amount of a strong base?
Okay, so there are 2 ways to make it. Rohit has given you one. Okay, it's frozen and muted, so we'll see if I can ever get it out of there. He says that if you were to take ethanoic acid, like 1 mole of it, whatever, and you added half as much of a strong base, a reaction would occur. The acid would give its proton to the base, and we would make water and ethanoate. And if we set this up as a RIF table, because God knows you guys like a good RIF table, we could say that we started with 1 sorry, I don't know how to do them anymore. A RIF table. We could say that we started with 1 mole of this and half a mole of that. Remember, I always put units in RIF tables to remind myself that this isn't equilibrium. This is just straight up limiting reactant talk. What is the limiting reactant? Yeah, like Mohab told me to put in half as much. He chose the limiting reactant. He said half as much. He knew there was less of this, and so let's believe him. Let's use it all. If we use all of this, we're going to come over here, and we're going to have half a mole, because there's a 1-to-1 ratio. So if we subtract a half here, how much do we subtract here? Oh, okay. And so if we come over here, how much of this do I make? And so we will have half a mole of this. And so Mohab's idea about how to make a buffer was to put in half as much of the strong base as we had of the weak acid, thereby converting half of the weak base into its conjugate, half of the weak acid into its conjugate base. So that is a buffer system. Is there another way we could do it then? I'm keeping ethanoic acid. True statement. Is there any other ingredient that we could add? Thinking about people who added it. Amarachi certainly added it. You added it. Salt. We could just directly add the salt. And so instead of adding half as much of the strong base, we could add an equal amount of the salt. So we would just go directly here. So that's what I'm going to do on this board. So I'm going to have exactly as much. So I added sodium ethanoate. Sodium is a spectator ion, it's floating free in the solution, it's doing nothing remotely interesting, but I'm going to start with a system that is, per Mohab at least, a buffer. It has approximately equal amounts of an acid, a weak acid, and its conjugate base. So my initial conditions have changed. In changing my initial conditions, does the change line change? No. Just going to go with a no. But this line would change, because the equilibrium is how much I started with and then how much it changed. So it's going to be 0.3 plus x. So y'all are going to come over here, and we're going to calculate the pH of this. So you would say it's the concentration of ethanoate. That's going to be 0.3 plus x times the concentration of hydronium, that's just x, over the concentration of ethanoic acid. Everyone cool with that? Do you think I'm actually going to solve that quadratic? What am I going to do, Raimi? I'm going to assume that x is small compared to the initial concentration. I'm going to assume that both of those x's are negligible. Then I got 0.3 over 0.3, what's that? That's 1, so x is equal to 10 to the minus 4.75. But x is also the concentration of hydronium.
So x is 4 points.
No, x is 10 to the minus 4.75. The pH, I think you're just a step ahead of me,
Yeah.
is 4.7.
Yeah.
At the half equivalence point, that's what this is, the pH is equal to the pKa. Again, paper 2, that's the only place you need to do the calculation. At the half equivalence point, when the amount of weak acid is equal to the amount of its conjugate base, the pH is the pKa. Done. Did nothing. But I want to go back to this formula, and I want to think about this approximation. Before, we said that taking 0.3 minus x and rewriting it just as 0.3 was admitting to each other that we just used the initial concentration of the ethanoic acid. It seems to me then that we can admit to each other in this new buffer calculation, we did something different. We also took 0.3 plus x to be equal to 0.3. Or we also assumed that the amount of this thing was essentially the initial amount. That is the Henderson-Hasselbalch equation. Like, that's all they did. They said, make this approximation right there. But the reason that you're getting questions wrong, if you're using it in the wrong place, is because in our last problem, this value was x. We couldn't assume that it was 0. That would be wrong. That would be crazy. Okay. So let's rearrange that for a minute. See how easy the problems can be. How much you wish that this was in topic 18. I'm going to take minus the log of both sides. Does anyone have a fun nickname for minus the log of the Ka? Thank you, Raimi. And now I'm going to take minus the log, but in my head at least I have a product. I'm trying to divide the two, I'm trying to separate the two things that are multiplied. So I have this term, this ratio, and I have this term, the H3O plus. Could you guys help me remember what the log of A times B is? So the log of A times B is equal to the log of A plus the log of B. So I'm going to write that here. I'm going to say it's equal to minus the log of this ratio. Minus the log of the concentration of hydronium. If you're asking yourself why is it minus, it's because I took minus the log of everything, so I had to distribute the minus sign between the two terms. If you're asking why did I peel off this point, it's because I'm going to say, yo, what is minus the log of the concentration of hydronium? It's the pH, and you just derived Henderson-Hasselbalch. That formula's free. How many more times in your life do you have to derive it? 0 for me. We're done. But the reason you have to know when to use it is because you're assuming that you have viable, non-zero, reasonably equal amounts of both the acid and its conjugate base. And if you don't have that, you're making an approximation that's erroneous and you get like wackadoo answers. So again, if you're sitting there on paper 2 and you're like, F, this is one of them acid-base problems, I don't know how to do it. I don't know how to do it either, but don't use this equation, right? Like, I know how not to do it. So don't go there, you're gonna be stuck in this world. Just do your best to plug something into a Ka expression. Yeah. So because the formula is free, the questions have to be like a little bit trickier than what's the formula. Is everyone okay with writing it that way? How would I identify what a base and an acid were if it was not ethanoic acid? We're like, gosh, she's been asking me that same question for a year now. Like, I know ethanoic acid is an acid. What would you look for? What are some hints I might be acidic? A positive charge, the presence of protons. And a hint that I might be the base is a negative. Do you think that we can only do this for acidic buffers? No. Like, I assume that someone smart enough could do this for a basic buffer, and so if you wanted to think about it for a minute, you might be able to write that expression for Kb down. I don't know how you feel about Kb. No one likes working in base world. Does that look good or not? Does that look like tears or sadness? Or yes, that makes sense? All of the above?
No, it just looks odd. It's fine.
Okay, so I'm thinking about like ammonia, that's what I call B, is being hydrolyzed. It's making ammonium and hydroxide. So this is BH plus. Karthik said that the proton, Brecken said that the plus sign would be a hint that it was the acid, hydroxide is the base. And then we have that original base here. So if we were to make that same Henderson-Hasselbalch approximation, we could say that the pKb is equal to the pOH minus the log of the concentration of the acid over the base. This is not going to surprise you, but I can't remember that. I don't know if you can. Like, I can write this and take minus the log of both sides because that's a skill I have. But remembering this is not a skill I have. My expectation is this is the one you need. But again, my expectation is that this is written in the data booklet. So if they wanted to ask me something creative, maybe they would ask me, how do you generalize it for a base? And so let's look at the similarities and differences. The A turns into a B, the H turns into an OH, the conjugate base turns into the conjugate acid, and the weak acid turns into the weak base. So it's a 100% flop. There are no sign changes. It's just every time you used to say acid, you now say base. So again, that's why I think it's reasonable, but I think it could be gross, unfortunate. So I'm going back to the normal form because all of our amino acids are in fact acids, and I think that's the form they're going to talk about. And so what I have is I have serine. That's one of your 20 amino acids in the data booklet. And it has 2 pKa's. And they are at 2.2 and 9.1. And I would like to calculate the pH of a solution that contains 0.8 molar Zwitter ion and 0.2 molar anion. So again, the question is calculate the pH of an aqueous solution that contains 0.8 molar Zwitter ionic serine and 0.2 molar anionic serine. What are we going to do? What is the hard part? Or what is the easy part? I don't think we're going to average the pKa's, but I think you guys have identified what's tough. What's tough is that we have 2 pKa's, but we only have one system. And so we have to imagine which one matters to us right now. And so remember, in between these two, I have the Zwitter ion. Here I have the cation. The A was the wrong word, I was going to say acid, but A is right out. Here I have the cation, the fully acidified. It's going to lose a proton to become the Zwitter ion. Here the Zwitter ion loses a proton to become the anion. So which equilibrium are we working in if we have the Zwitter ion and the anion? So which pKa do we use? So now we're done. So the pKa is 9.1. It's equal to the pH minus the log of the concentration of the base over the acid. I recently learned that I should look for a negative sign for a base, so I'm going to choose this one as my base. So I'm going to put 0.2 over 0.8. Does it make sense? Does it make sense that the pH is going to be greater than 9.1? Yes. Does it?
You guys have 4 of those, right?
Oh my God, no, we're good.
Because like the log is so, it's a negative, and then it becomes positive, and then it makes
Thank you. So like Audrey knows that I struggle a lot with this sign. So So I'm just trying to make sure that my answer makes sense. I don't know how to do algebra. The minus and the minus is a plus, I got there. But when the plus comes over here, it's gonna make it smaller than 9.1. At what concentrations would this be 9.1? What would I expect about them? When is the pH equal to the pKa? When they're equal. But this one is tilted toward the acidic side, the zwitterion, so it should be less than 9.1. So I was trying to check my work to make sure I didn't make a stupid sign error because I'm so very good at it. Let's get an answer and put us out of our misery. I got 8.5. It's a happy face because it's the way I expect. Okay? What is the pH if you add 1 gram of sodium hydroxide to 1 liter of water? I wish I had a film of what I'm doing. Like, you're low key. I don't know, it was very like. Anyone? Who's the best we're gonna see? We'll have for like a month. So I hope what you did was you took 1 gram of sodium hydroxide and you looked on that beautiful periodic table and you said sodium's 22.99 and oxygen and hydrogen is 40 grams per mole. So you had about 0.025 moles of sodium hydroxide, which is a fancy way of saying hydroxide. And then I hope what you did was you said, well, if I have this many moles in that many liters, the concentration of hydroxide is just that many moles over that many liters, that same number, and minus the log of the concentration of hydroxide is the pOH. I got 1.60, but I asked you what is the pH, so I hope that you subtracted from 14 and got 12.40. Okay, that is a paper 2 question. Let's turn this into a paper 3 question. And instead of adding the sodium hydroxide to water, what do you think we're going to add it to? We're going to add it to a buffer. What?
What's this have to do with protein?
These are amino acids. They're buffers. So here's glycine. Glycine also has 2 pKa's. One is at 2.3. The other is at 9.6. I have a 1 decimeter cubed solution that contains 0.4 moles of the zwitterion. And it contains 0.16 moles of the cation. And I would like to know the pH upon adding 1 gram of sodium hydroxide. Is this too much joy for this early in the day? I don't know. Then we go on to kinetics. I just did what we did for the other problem while I was hoping you were working on this new problem and found that the initial pH before we put the sodium hydroxide in was 2.7. You agree with that? Do you know the answer for this?
I got an answer from
Okay.
the initial, right? Wait, isn't the initial
I used this equation. I chose the pK that I thought was appropriate, which was 2.3, because I have the zwitterion and the cation this time. I put in these two concentrations, and I got 2.7 to get the initial concentration, which I didn't ask you to do, because I thought it was the same as the last problem. I was just gonna see how much it changed, and I thought you might like to know where it started. So that was just for free while I was trying to give you some time to do your hard work. Just a lot of deer in headlights. Yes, ma'am. So when we add the 1 gram of sodium hydroxide, what happens? By a base? I think I'm gonna make more zwitterion. I think I'm gonna convert cation into zwitterion. So, if I were to write this down, the reaction that we're doing is the zwitterion. I can call it Z or I can call it gly. What do you like? Okay, I'm actually gonna have to call it H gly. Lies, all lies. I'm just gonna draw it out so I don't have to call it anything. Glycine's everyone's favorite amino acid. Okay, so I drew that out. I could also say Z plus hydroxide. Can't say that. I can say C plus hydroxide makes Z plus water. So if that's my reaction, again, I feel like the base is going to neutralize the most acidic thing. The most acidic thing is the cation. Then I claim that this is a reaction that goes to completion, as all neutralization reactions are. And so if I began with 0.16 moles of the cation, 0.025 moles of hydroxide, and 0.4 moles of the zwitterion, that all of the sodium hydroxide would react. And when all of it reacted, what it would do is it would use up exactly that amount of this. So we would be at 0.135, and 0, and 0.425 as the moles. We care that we have a liter of this solution in a minute, because we're going to need to know the concentrations to plug them into Henderson-Hasselbalch. But right now, I'm just treating this as a limiting reactant problem. I would call this a RIF table, because I like to really aggregate as many people as I can in a day. And RIF tables are always in moles, so I'm not yet worried about the water. So in my calculator, what I did was I rearranged this because it's clearly in the wrong direction, and you already saw that I can't subtract. I knew that I was working with the pK that's 2.3 because I had the cation and the zwitterion. And so I wrote that the pH was equal to 2.3 minus the log of the concentration of the base over the concentration of the acid. I know I haven't closed those braces. That's because initially, when I calculated the pH to be 2.7, that's what I took. But finally, what I did was I said that the base is going to convert acid into conjugate base. So this number is going to get smaller by 0.025, and this number is going to get bigger by 0.025. So that's what I honestly typed in. But we all have the impression I've done a whole lot more buffer calculations than you have. Apparently at some point in my life that was really important. It's not just once every 3 years that we teach option B. Like, it must have been something, because that seemed like a natural approach, but this is where it came from. When I solved that, instead of getting 2.7, I got a pH of 2.8. So how much did the pH change? By 0.1. How much did it change the pH of pure water to put this 1 gram of sodium hydroxide in it? Remember over here, we added 1 gram of sodium hydroxide to 1 liter of water, and we got a pH of 12.4. So over here, the change was from 7 to 12.4. And here, the change was 2.7 to 2.8. It's a buffer. It resists change to pH upon the addition of small amounts of acid or base. Yeah. So,
Isn't it?
sure is. Good thing I typed it in my calculator, right? Thank you. Take a better picture, Chem March. Don't embarrass me. So buffer capacity is a measure of how good a pH is at resisting, how good a buffer is at resisting change in pH. And one way of thinking about that is how many moles of sodium hydroxide could I add to make this change by 1 unit? I don't think that we need to do calculations of this. These two numbers are gonna be the same. You can imagine that you get an equation that's kinda unwieldy, but, you know, if Ramy helps me with the signs, maybe I could get it right. But buffer capacity is asking something about how hard it is to change the pH. So this buffer absorbed 1 gram of sodium hydroxide. Would it absorb 10 grams? Well, in the numerator, we would have 0.4 plus 0.25, that's okay with me. But in the denominator, I would have 0.6 minus, uh-oh, that's a negative number, that's a failure. So clearly, we have exceeded the capacity of this buffer if we had 10 grams. But there must be some point in the middle of those two extremes, 1 gram and 10 grams, where we exactly change that pH by 1. What would make something have a bigger buffer capacity? What broke? Why couldn't we absorb the 10 grams? What did we perhaps not have enough of? So what if these initial concentrations had been 1.6 molar and 4 molar? Could we then have absorbed 10 grams? Yes. And so the buffer capacity is a fancy way of saying how concentrated is your buffer. If you have a whole lot of the salt and the conjugate, and it's acid or base, whatever. If you have a whole lot of the two ingredients, then you can absorb more change. The buffer is both of them. So I'm saying if I wanted to increase the buffer capacity, what I would do is increase the concentration or the amounts of both ingredients. I don't want to change the ratio. Apparently I wanted this pH to be 2.7. But if instead of having 0.4 and 0.16, I had 4 and 1.6, I would have a higher buffer capacity. I could put more base in there without really changing the pH. It could absorb 10 grams of sodium hydroxide instead of just 1. So that is what buffer capacity means. It was on one of the early slides. Do you have one more of these in you, or should I save it for next time? One more? So we're still going to talk about glycine. Shame I erased it. Glycine still has 2 pKa's. The first one's at 2.3, the second one's at 9.1. I have a solution where I added 0.5 moles of glycine to 1 liter of water, 1 decimeter cubed of water. And I set the pH to 5. I'd like to know what is the concentration of all of the glycine species. So there could be cation, there could be anion, there could be zwitterion. What species are present? And how much of them, what is their concentration? So what is the concentration? So what glycine species are present? Yeah, I was gonna write cons, and then I was like, I could give them a few more letters, but I just couldn't fit them all. Ooh, I should take a 10. call this number 0.5 minus x. I claim that you have to call this a reasonable number. Because there are only so many pens in there. So, I'm gonna put 3 pens for the glycine.
Oh.
Now, I don't actually know if this glycine is protonated or deprotonated, it just came from a jar. But I used pH stuff to make this solution 5. And you guys were able to use this formula to tell me that the ratio of pen cap on to pen cap off was 2 to 1. Is that fine? Like, you believe you can get this ratio? I mean, you have the math, right? Like, you just call that a variable and take the ratio of the two forms. My claim is that in addition to knowing the ratio is 2 to 1, you know the sum of them because you know how many pens you put in there. So if I call this 3 minus 2, what do I have to call this? Okay, so if you call this 0.5 minus x, what do you have to call the other one? Okay, 'cause they have to sum to the 3 pens. That's surprising. I hear you. I'm just trying to put a cap on a pen. And, you know, that was harder than I expected. No, now you have one equation with one unknown. me know if you agree. Is this a good buffer? So we're changing it by 2.7. It's not a good buffer. You can see that here. These amounts are approximately equal. They're 5 times. Yeah. Good answer. That takes up the math part. I don't know if I solved it in the most elegant way. I liked what you were doing, just making it one equation. Okay, and a tricky for those of you who are thinking about what are some things that could make this easier. Both of the ingredients of a buffer, both the base and the acid, whatever they may be, are in the same container when you're measuring that pH. So their volumes are equal. And so if you think about this concentration as being the number of moles of base divided by the volume, we're ratioing that to the number of moles of acid divided by that same volume. Those volume terms cancel. And so occasionally, just that realization can make a problem a little bit easier. I don't have an example, nothing came up here, but if I'm thinking about like a tricky thing that you may not have considered because you've been doing this for like 30 minutes, maybe an hour. Again, that hasn't helped us yet, but just realizing that the concentrations of the base and the acid could also be considered just as their number of moles. It could save us a little bit of work if the volumes weren't all so politely a whole decimeter cubed of water. So, just a thought. This problem has been on a test. So this sort of 2 equations, 2 unknowns from my perspective, I don't know what it is from your perspective, has been on a test, but that was a test quite a long time ago. So I think that's why we still look to it, but I don't know if it's a realistic thing on the test you will be taking. I will give you all of the paper 3s, I will keep no secrets from you, but it certainly has been there. Mohab?
Is there a way to do this with like a price table or something? Or like something like that, or a riff? Or like with an equation?
Equation.
Like a kind of, I don't know.
Yeah, I hear you. Okay? So Mohab has challenged us. Honestly challenged us to figure something out. He's imagining that he has the cation. I'm just going for that. Is adding water, and it's going to be in equilibrium with the Zwitter ion and hydronium. And he's imagining a solution where he has added 0.5 molar. Yeah, I think you've done this. You've added zero. I don't know if I can do this. Like that's the real answer. So you're imagining that I've added 0.5 moles of this, right? That's what we're told in this problem, that we have
Yeah,
0.5
that's
moles
why.
or molar glycine. And so we know that some of this will hydrolyze and we'll be left with less of it. And so we can come over here and say that we'll make more of these 2 things. And that's that's still fine, right? But we're told that at the equilibrium that we achieve, that this is 10 to the minus 5. I don't think we're gonna get it right. So I think that if you believed that, you would say that this number is 0.5 minus 10 to the minus 5, and this number is 10 to the minus 5. And that's just not quite, it is what we got. It is what we got. I'll do it that way.
You assign X as.
Okay, so
Oh, because we know that the.
since the pH is 5,
Yeah, then it has to be.
we know that at equilibrium, that is the concentration. If that's the only way we can make it, that's the assumption we make, we don't look at the water at all, then we know that we must have 10 to the minus 5 moles of this, because those two have to be equal. Well, that seems like ridiculously easy now. Do you agree?
Yeah, it gives us the amount to litter on.
And to the amount, so we have zwitterion being 1 times 10 to the minus 5, 9.96 times 10 to the minus 4 seems like the same number. And this is 0.5 minus that, which can be 0.499, and I just didn't give you enough digits.
Yeah.
Yeah, I think that's it. Okay, smarty pants. Whole point of this is buffers.
Yeah. No, this is a kind of.
Why is our insert kind of wrong? You're wondering not why it's wrong, I'm thinking. I'm asking for why is the 9.96 on that board different than the 1 times 10 to the minus 5? Like there's a 4% discrepancy, 4,000%. I'm not looking at sig figs, I was just 4,000, 4.4%. Neither of these worried about the water. I think the pKa is fine. I think it's because Moheb didn't make me make any approximations about something being small compared to something else, or something being negligible compared to something else. But by virtue of using Henderson-Hasselbalch, we're using the initial concentrations of these things, and you can see that they're really far out of whack, and there's not a whole lot of this here, so I'm not really in a buffer zone. And so it's conceivable that the Henderson-Hasselbalch equation is kind of breaking down a little bit. Normally, we try to keep these two things within a factor of 10, maybe 100 of each other. And when we're at 501 for our calculation, we're no longer really in a region where we should be bothering with Henderson-Hasselbalch, but this unit is Henderson-Hasselbalch, so we did it. And so we're starting to see that maybe there is a little bit of error creeping in, and so that, a little bit, I'm gonna stick with 0.4%, so maybe I'll stop looking at me like I can't math, is perhaps the error associated with using that approximation. Thanks for giving me something to think about. I won't talk about that tomorrow. Why what?
Oh, wait. This, right?
Oh.
There's some.
Oh my.
Like the cation is.
Oh, it's just because I put him in the wrong place and y'all are, no I didn't. Okay, then I don't know. Why is it wrong, Mohab?
I don't know.
Cation plus water makes the zwitterion plus hydronium. Yeah, that's quite wrong. Yeah, Mohab, you suck. So, okay, what I'm hearing, and please correct me when I'm wrong because I feel super nervous, is that you're saying someone has tuned the hydronium ion concentration independently. And so I can't make the assumption that I made that both of these x's are the same. Like, I figured out what the pH would be in the wrong circumstances, like just if glycine naturally did this in solution. But you're saying that you set this to 10 to the minus 5. Is that correct?
Yes, yes.
And so what did you do after that?
5 equals 2.3.
Okay, 5 equals 2.3 minus the log.
Or plus the logs. I did the equation. So 0.5 minus x squared.
Okay, that's what Ray mean. Okay. I agree with you. Do you agree with her? Do you see what I did wrong, like assuming something that I could not assume?
I was just initially confused by this way. It's not like,
Does this help?
yeah.
So I, like, try to think of it was just seeing that 0.5 minus x and x that I was working so hard to convince the back table of. But what I did incorrectly was assume that this was natural, but we knew it wasn't natural because someone set that pH to be 5. And so when we magically got the right answer, like I felt like you were the rock star. But you have to do all the same work. You didn't find some like fly shortcut, save us all. And so you're gonna be in the same position. You're gonna have 0.5 minus x over 0.5 is equal to 10 to the 2.7, which is 501.
And there will be
Yeah, back there.